Hi everybody, as you can see I've moved indoors and I'm actually now in Dr. Kim's lab, and there's a really good reason why I'm here in Dr. Kim's lab, because I'm going to talk about the importance of the connection between experimental data and what we're going to try to do with chemical kinetics. So I'm just going to put the iPad down here so I can write on it, and so we're going to focus in on the inseparable connection between data and kinetics. You really can't do kinetics until you have your hands on some experimental data. The connection is absolutely essential. And so let's talk a little bit about the kinds of data we can collect in chemistry. Think about it for a moment. If you are an experimental chemist, what kind of information can you collect about a reaction? It turns out there's not a whole heck of a lot of information you can collect, or put another way, a lot of different variables you could control. For example, you can control, say, the concentration of your reactants. More importantly, you can really only control the initial concentration of the reactants. So you can set the system up to work with, 1.2 molar of some starting reactant. Or we could control pressure if we're working with gases. That's the same thing as concentration. And the other thing we can kind of control is temperature. Outside of initial concentration and temperature, there's not a whole heck of a lot we experimental scientists can really control when we're working with our chemical systems. Yes, we decide what experiment we're going to run, we decide, what kind of a synthesis we're trying to do, but in terms of the experimental variables, it's really down to concentration and temperature. So if we're going to try to understand reaction rates, then we're going to need to understand reaction rates in terms of those variables that we can control, namely concentration and temperature. So it turns out that there's really only a couple of different ways we're going to describe chemical systems when it comes to chemical kinetics. And the different ways we describe chemical systems using kinetics, these concepts are referred to as rate laws. And a rate law is simply, how does the reaction evolve depending upon the particular experimental conditions we can control. And there are two types of rate laws. One type of rate law is called the differential rate law. And this rate law will describe the chemical system and how it behaves kinetically in terms of concepts like concentration and temperature that I was alluding to before. So if we change the concentration of our reactants, we can see how that change of concentration will affect the rate of the reaction. Or if we do the reaction at a different temperature, we will be able to use the differential rate law to determine what kind of an effect that has on the speed or rate of the reaction. The other kind of rate law that we're going to look at in this unit is the integrated rate law. And this is the one that will bring time in as a variable. At this point, time becomes important. So, for example, I might ask, how much product is my reaction forming after 4.5 minutes? If I want to know the answer to that, I appeal to the integrated rate law. Or maybe I need to know, say, the half-life of a particular radioactive material. Half-life is a concept I'm sure most of us have already heard before, and it's a chemical kinetic concept, right? The half-life is the amount of time it takes for your initial concentration of reactant to be cut in half. And that comes out of analyzing the integrated rate law for the loss of radioactivity in most cases. So these are the two big rate law concepts that we're going to go after. And we can only go after them, however, once we have experimental data. Okay? No data, no rate law. The rate law comes exactly straight out of all the experimental data. And it's the next videos that are going to explain how we derive these rate laws, and we're going to start first with the differential rate law next time.